In this lecture series, you'll be introduced to NMR spectroscopy, or nuclear magnetic resonance spectroscopy. And like IR spectroscopy, this is a spectroscopic technique that we use to help us characterize molecules or to figure out what we made when we run a reaction. In all spectroscopies, we're basically irradiating our sample, our organic molecule, with light or energy and watching its response to that irradiation. The various kinds of spectroscopies differ in the wavelength of the light or the energy of the light that we're using. In IR spectroscopy, we're irradiating our sample with light in the infrared region of the spectrum. In NMR spectroscopy, we're using radio waves with a much lower energy, and that means we're measuring very small energy differences. And in NMR spectroscopy, the energy differences that we're measuring are the energy differences between two nuclear spin states. Different nuclear spin states exist in the presence of a magnetic field. So in NMR spectroscopy, we apply a magnetic field to introduce those differences. Then we pulse our sample with radio waves and watch or measure the response. What we're measuring with NMR spectroscopy is very tiny energy differences, the change in nuclear spin states. And what we'll see is that NMR is much more information rich than IR spectroscopy. A single NMR spectrum can tell us a lot more about the structure of the molecule than a single IR spectrum can. The ability to measure an NMR spectrum relies on nuclear spins. And the nuclear spin is a property of the isotope, not the element. It depends on the mass number, not the atomic number. And the presence of a nuclear spin requires either an odd mass or an odd atomic number, or both. The number of allowed spin states is determined by I, the nuclear spin quantum number. And what I'm showing you in the gray box are some common values of I, ranging from 0 to 1/2, 3/2, 5/2, and so on. Then I'm also showing you the isotopes that correspond to those values of I, those nuclear spin quantum numbers. We just noted that we need either an odd mass or an odd atomic number. So this first row, with even values for both and a spin quantum number of 0, are not NMR active. They will not show any absorbances if we irradiate with radio waves, because there are no nuclear spins to undergo spin state changes. In contrast to the row I have highlighted in blue, with a spin quantum number of 1/2, these are NMR active nuclei. And they're some of our most common NMR active nuclei, and they include proton, carbon, nitrogen, fluorine, and phosphorus. And note that for carbon, carbon-12, our most abundant isotope of carbon, is NMR inactive. But carbon-13, which does have some natural abundance, is NMR active. So when we measure a carbon NMR spectrum, we're measuring a carbon-13 NMR spectrum. And this notation with the mass number included is how we denote different types of NMR spectroscopy. And the two that we'll focus on in this class are proton NMR spectroscopy and carbon-13 NMR spectroscopy. And we'll begin with proton NMR spectroscopy. And what you're seeing on this slide is a typical proton NMR spectrum. And there are three key features of peaks in a proton NMR spectrum. And these are the chemical shift, the integration, and the multiplicity. We'll introduce each of these features briefly now, and then we'll discuss them in more detail in the next videos. The first feature is the chemical shift. The chemical shift is the x-axis of our spectrum, and it tells us about the environment of a hydrogen. It tells us if that hydrogen sits on an sp3 or sp2 hybridized carbon. And it tells us if that proton is near an electron withdrawing group. The chemical shift is measured on the delta scale in units of ppm, or parts per million. And these days, in modern NMR spectroscopy, the chemical shift is measured relative to a standard compound, and that standard is tetramethylsilane. This is a silicon with 4 methyl groups bound to it. And tetramethylsilane, or TMS, is set as the 0. So by convention, it has a chemical shift of 0. All other signals are measured relative to TMS. And the chemical shift value of a peak, or a proton, then, is described as the observed shift from TMS, and that's in hertz, relative to the spectrometer frequency, and that's in megahertz. So our units here are hertz over megahertz, and that gives us our parts per million units on the chemical shift value. And the third feature that we'll see is the multiplicity of a peak, or spin-spin splitting. And the multiplicity, the splitting, is how many lines a particular peak has. Let's look at the peak at 1 ppm. This peak has 3 lines, and the middle line is larger. We call this a triplet. The peak in the middle of the spectrum has 4 lines. We call this a quartet. And the peak near 5 ppm shows 1 broad line. We call this a singlet. As we learn more about NMR spectroscopy, we'll see that these 3 features, the chemical shift, the integration, and the multiplicity of the peaks, they give us a map of a molecule, and they allow us to draw a structure of an organic molecule from the spectrum alone.